Hello, welcome to the penultimate CHEM271 tutorial. So this will be a practice final. So this will only cover metabolism. Specifically, this one will only cover gluconeogenesis to the end of the electron transport chain. This will not cover glycolysis. If you want to see glycolysis problems, go watch the video that I made on glycolysis. Also, there are some things in here that will be repetitive with the previous videos I've made on metabolism. Therefore, I might not cover some of these topics again in a lot of detail. So I recommend watching the 6 videos I made on metabolism covering glycolysis, gluconeogenesis, glycogen metabolism, the citric acid cycle, and the electron transport chain ATP synthase. Okay? So we're going to start with question 1. So question 1 is asking, in gluconeogenesis, how is oxaloacetate transported to the cytosol? So essentially, in gluconeogenesis, this is the conversion of pyruvate to phosphoenolpyruvate, right? So it's the reverse of the last step in glycolysis. So the way that this works in gluconeogenesis is that pyruvate used in this reaction is actually found in the mitochondria, specifically in the mitochondrial matrix. So that is where the pool of pyruvate is for gluconeogenesis. It is in the mitochondrial matrix. That pyruvate is converted into oxaloacetate by pyruvate carboxylase in the mitochondria. Then, in order to get this oxaloacetate out of the mitochondria, oxaloacetate cannot pass through the membrane directly. So the oxaloacetate must be converted into malate through malate dehydrogenase. And then through the malate alpha-ketoglutarate antiporter, that malate then can be transported into the cytosol. Okay, so this is very similar to what we saw with the malate aspartate shuttle. It's pretty much the same thing. It's the same enzymes and the same transporter. So it's very similar to the malate aspartate shuttle, okay? So oxaloacetate cannot pass the membrane, okay? But malate can. So oxaloacetate is made in the mitochondria, okay? And then it's converted into malate. Malate passes through the membrane in the cytosol. Malate is converted back into oxaloacetate through malate dehydrogenase. And then the oxaloacetate is converted into phosphoenolpyruvate with phosphoenolpyruvate carboxykinase. We've already looked at all these reactions in detail in previous videos. So here, oxaloacetate to PEP takes place in the cytosol, okay? So we're making the oxaloacetate in the mitochondria, and we're turning it into phosphoenolpyruvate in the cytosol, okay? So part B is asking, why is pyruvate to phosphoenolpyruvate a 2-step process in gluconeogenesis, okay? So I here have 3 reasons. So the first one is that in glycolysis, phosphoenolpyruvate to pyruvate is an irreversible reaction. So you can't just do the reverse of that reaction. You have to make it different in some way. So instead of doing this reaction, right, that is not reversible, the cell does a different reaction to get from pyruvate to phosphoenolpyruvate. It also has to input a lot of energy because the reaction phosphoenolpyruvate to pyruvate is favorable in glycolysis, but pyruvate to phosphoenolpyruvate just reversed is not favorable, positive delta G. So in order to make the reverse reaction favorable, a different reaction is used that utilizes quite a lot of ATP and GTP. So about 2 ATP and 2 GTP per glucose, 1 ATP and 1 GTP per pyruvate. Remember, 2 pyruvate are needed to make 1 glucose, right? So this reaction is irreversible in glycolysis. A different reaction needs to be used, and that new reaction happens to have 2 steps. But why does it specifically have 2 steps? So this is preventing a futile cycle. We'll describe this a bit more in the next question, but a futile cycle is essentially a reaction that is reversible, where once a product is made, it is completely used up because the reaction is reversible. So if glycolysis and gluconeogenesis were sort of the same thing, if they weren't regulated in some major way, as soon as pyruvate was made by glycolysis, it would just be converted right back into phosphoenolpyruvate in gluconeogenesis. So by having this two-step process, we are sort of preventing this futile cycle where as soon as we make pyruvate, we immediately use it up in gluconeogenesis, meaning no net change in the concentration of either of these, which would not be good for the citric acid cycle, which requires pyruvate. Okay? So because these two reactions are regulated differently, it essentially means that you can have the buildup of one or the other product. You won't just have the same concentration of both sort of stagnating. But we'll look at that in a bit more detail next. For this last part, so the last sort of indicator of why pyruvate to phosphoenolpyruvate in gluconeogenesis is a two-step process is because in glycolysis, the pyruvate is made in the cytosol. So we have phosphoenolpyruvate getting converted into pyruvate in the cytosol. However, in gluconeogenesis, as we see here, pyruvate getting converted into oxaloacetate is actually done in the mitochondria. So what this means is that we have two different pools of pyruvate. So these reactions don't interact. So the pool of pyruvate in the cytosol used for glycolysis does not impact the pool of pyruvate in the mitochondria used for gluconeogenesis. So why exactly is this two reactions then? It is to allow for these two different pools to exist so that they don't interact and they don't lead to futile cycling. Okay, so these two reactions exist so that one reaction can happen in the mitochondria and the other reaction can happen in the cytosol. So this allows for the formation of the two different pools of pyruvate. That is essential so that these two pools of pyruvate do not lead to just the straight up reverse of this reaction, which could potentially lead to futile cycling, wherein pyruvate is made in the cytosol and then pyruvate is immediately used up because it's the same pyruvate. Okay? So on to the next question now. All right, question 2. So this is a little bit redundant with the last problem, but here we're just asked to define futile cycling in part A. So futile cycling is when you have two opposite metabolic pathways occurring at the same time. So an example of that would be if phosphoenolpyruvate was converted into pyruvate in glycolysis, at the exact same time pyruvate was being converted into phosphoenolpyruvate in gluconeogenesis, like we saw before. So if these are happening at the exact same time, there is no net generation of either pyruvate or phosphoenolpyruvate. They're both being used up, which means there's no net pyruvate generation or there's no net glucose generation. So you're not making glucose with gluconeogenesis, you're not making pyruvate with glycolysis. They're just happening at the same time and they're kind of using each other up, so you don't get any net generation of either. So you can't make glucose if you need it, you can't make ATP from glycolysis if you need it. Okay, so if these are happening at the same time, that's really bad because that means that the cell can't move in any one direction in terms of its metabolism. It can't make glucose, nor can it make ATP, which it needs to do those at different times under different circumstances. Also, if both are running at the same time, that leads to a huge loss of ATP because gluconeogenesis uses a lot of ATP. So the question, part B, is asking, so in glycolysis and gluconeogenesis, how does the regulation of PFK1, phosphofructokinase 1, and FBPase2, fructose bisphosphatase 1, so how does the regulation of these prevent futile cycling? So here, remembering glycolysis, fructose 6-phosphate is getting converted into fructose 1,6-bisphosphate by phosphofructokinase 1. So this is activated by fructose 2,6-bisphosphate, not fructose 1,6-bisphosphate, fructose 2,6-bisphosphate. It's activated by AMP, it's inhibited by ATP, inhibited by citrate, inhibited by H+. If you want more explanations for this, go watch the videos on glycolysis and gluconeogenesis that I have made. For fructose bisphosphatase, this is wrong. Fructose bisphosphatase 1, it is inhibited by fructose 2,6-bisphosphate, inhibited by AMP, activated by citrate. So notice how here we have activated by fructose 2,6, activated by AMP, inhibited by citrate. Here we have inhibited by fructose 2,6-bis-P, inhibited by AMP, activated by citrate. These are opposite, meaning if we have a lot of fructose 2,6-bisphosphate, for example, that will lead to the activation of glycolysis and the inhibition of gluconeogenesis. So the fact that they are allosterically regulated in different ways, they have opposite regulation in terms of their allosteric. That means only one of these processes is going to be active at a time, right? If you have a lot of fructose 2,6-bis-P, you're going to activate glycolysis, inhibit gluconeogenesis. So only one of these can be running at the same time because of this opposite regulation, meaning the cell is either making ATP with glycolysis or making making glucose with gluconeogenesis. It's not doing both at the same time. Otherwise, you get this futile cycle that has no net production of either product and a net loss of ATP. Okay? So the second part of this question that I didn't write is how does this relate to phosphofructokinase 2 and fructose bisphosphatase 2. So if you want a much more detailed explanation of this part, go watch my video on gluconeogenesis. I go into this in a ton of detail and show all of the reversible phosphorylation. But here, just the summary of this is that at high blood glucose, fructose 6-phosphate is converted into fructose 2,6-bisphosphate. So if we have a lot of fructose 2,6-bisphosphate at high blood glucose, this activates glycolysis, right? So this is glycolysis, and this one is gluconeogenesis. Okay, so if we have a lot of fructose 2,6-bisphosphate, that activates glycolysis. So we want that. If we have a lot of glucose, you want to get rid of that glucose, so you activate glycolysis through this mechanism. And the enzyme that does fructose 6-phosphate into fructose 2,6-bisphosphate is phosphofructokinase 2, which is a kinase, right? At low blood glucose, though, fructose 2,6-bisphosphate is converted back into fructose 6-phosphate. So what this means is that you have a decrease in fructose 2,6-bisphosphate, which when you decrease that, PFK1 is less active and FBPase1 is more active. So this leads to sort of an increase in the level of gluconeogenesis. And the enzyme that carries this out is fructose bisphosphatase 2, which is the phosphatase. Remember, these are one enzyme with two different subunits that have two different catalytic functions. So essentially, at low blood glucose, you have more gluconeogenesis to make more glucose. So that is how the cell is regulating this and making sure that only one pathway is active at a given time and that that pathway corresponds to the level of blood glucose. That is done through the PFK2 and FBPase2 protein complex, okay? That does it for this question. Okay. Question 3. Why is water H2O excluded from the active site of glycogen phosphorylase? So glycogen phosphorylase is taking glycogen and it's using a phosphate group to take off one glucose from the glycogen to make glucose 1-phosphate and then leaving behind glycogen with one less glucose. Okay? So looking at the structure of this enzyme, it is a homodimer, so two identical subunits, and within each domain there is an active site that is sort of deep embedded within the domain, and when glycogen binds, these two sort of subunits close in on each other. So like they close in, and then doing that, the crevice between them narrows, and that is used to exclude water. So when the sort of two dimers, or the two subunits of the dimer come together, no water can enter, okay? So why is this important? So this prevents hydrolysis. So let's look at this. So if we go through phosphorylation, like here, we make glucose 1-phosphate. Glucose 1-phosphate can be converted directly into glucose 6-phosphate. And this can enter glycolysis, of course, right? However, if glucose is produced just through hydrolysis, glucose is converted into glucose 6-phosphate by hexokinase. However, that uses an ATP, right? ATP is invested at this stage to phosphorylate glucose into glucose 6-phosphate, and then that can enter glycolysis. So with hydrolysis, an ATP is used up. With phosphorylation, no ATP is used. So here you actually save yourself an ATP and you generate one more ATP net overall because that's one less ATP that you're using in the prep phase. So that means you're only using one ATP in the prep phase with phosphorylation versus with hydrolysis, that will lead to 2 ATP being used in the prep phase. So less ATP generation overall. The other reason why glucose should be phosphorylated is because glucose 1-phosphate cannot leave the cell, right? It cannot pass through membranes with that phosphate group. It also isn't recognized by glucose transporters. So it has a really hard time getting out of the cell. It is trapped in the cell. So that means it can go more likely into glycolysis rather than leaving the cell, all right? So those are the reasons why water would be excluded. It is to prevent hydrolysis and encourage phosphorylation, which saves an ATP and prevents the glucose from leaving the cell after glycogen degradation. Okay. Question 4, is glycogen a reducing or a non-reducing sugar? So let's define what a reducing sugar is first. It is a sugar that can react with an oxidizing agent. So essentially, it can interact with a chemical that will cause this to be the reducing end of a sugar to be oxidized, essentially. So in order to do that, it must be able to form a linear structure in solution with a free aldehyde. So this is what an aldehyde looks like, okay? And then this aldehyde can interact with an oxidizing agent, which is something like water or phosphate that can donate some electrons and increase the number of bonds there with oxygen, okay? So glycogen is actually mostly non-reducing. However, there is one reducing end at the very center of glycogen. So glycogen, remember, looks like this. So essentially we have lots of like branching chains coming off of it. However, at the center, you have one reducing sugar. And this will be bound to a protein called glycogenin. So essentially, let's look at just a disaccharide here, so 2 glucose monomers. Okay, so here's the non-reducing end. So the carbon 1 here is bound to another glucose, while on this one, carbon 1 is an aldehyde, much like how you see in the linear Fischer projection of glucose, okay? So the reducing end can sort of break apart, turn linear, and have carbon 1 turn into an aldehyde, while the non-reducing end cannot do that because carbon 1 is bound to another glucose. So all of the branches here end in non-reducing. And then essentially, remember, glycogen phosphorylase can then come in, break this bond, and add on a phosphate group, okay? However, the reducing end are not exposed. They are bound to glucose, makes them less reactive, okay? So the branches end in non-reducing sugars. The only reducing sugar is at the very center of glycogen, bound to glycogenin, and then glucose is removed from the non-reducing ends, which are at the ends of these branches, okay? And that is because on these non-reducing ends, their aldehyde, their carbon 1, is bound to another glucose, so it's not available to react, all right? Next question. Question 5. What is the role of the pyruvate dehydrogenase complex? And give the full reaction. So pyruvate dehydrogenase, this is converting pyruvate into acetyl coenzyme A. And what this is doing, this is an irreversible reaction. So thus it is creating an irreversible link between glycolysis and the citric acid cycle. Pyruvate is at the end of glycolysis, right? Glycolysis. And then acetyl-CoA goes into the citric acid cycle, or tricarboxylate cycle, okay? So what else is this reaction doing? It's making NADH, right? That can go off to the electron transport chain to make ATP, right? And it is producing a high-energy thioester bond. So that is what this is. No, it's not all of that. This here is the thioester. right? Carbonyl, sulfur. And this is very high in energy, so when it is broken, it releases a lot of energy, and that energy is enough to provide acetyl transfer potential. So the acetyl transfer potential released, the energy released, is enough to bring 2 carbons into the citric acid cycle. So adding 2 carbons onto oxaloacetate to generate citrate, right? So this is what the reaction looks like. For these exams, you just kind of got to memorize every reaction of glycolysis, citric acid cycle, gluconeogenesis, glycogen, metabolism. You need to know it all. It's not that interesting to show off here. It's just the reaction. I've already gone over all of these reactions before individually. So pyruvate, this is the structure. Coenzyme A goes in, NAD plus gets converted into NADH, and acetyl-CoA is generated alongside ACO2. The next part of the question is, what is the role of E2? So I've already gone into all the different subunits of PDH and the full mechanism in detail in the citric acid cycle video that I made. Just to review though, E2 is dihydrolipoyl transferase. Okay, so that is the name of the subunit. There are 3 subunits, E1, E2, and E3. E2, dihydrolipoyl transferase. So essentially at the end of E1, at the reactions that E1 catalyzes, we have made acetyl lipoamide. So we've added an acetyl onto lipoamide from pyruvate, 2 carbons from pyruvate. So then what E2 is doing is it's taking the coenzyme A and acetyl lipoamide, and it is creating acetyl-CoA. It is taking those 2 carbons, adding on the coenzyme A, making the acetyl-CoA, and then that generates dihydrolipoamide. If you want to see the structures of these, go back and watch the citric acid cycle video that I made. Okay, so this is what is producing this thioester bond here. And the other important role of E2 is that lipoamide, which is bound to E2, it's a prosthetic group from E2, carries substrates between all the different active sites, so E1, E2, and E3. It's sort of, so if we have E2 here, right, this is the lipoamide, and then it can carry the reactant here between E1 and E3. So it can bring the reactants between all of the different subunits. So that sort of facilitates this reaction. It increases the reaction rate because it is bringing the reactants in direct proximity with each other. It's moving around between the different subunits, kind of like a little arm that's carrying the reactants between the different subunits, right? So increasing the reaction rate because it's able to directly make the reaction happen. It's able to directly move around different compounds, different substrates, without the need for diffusion, and it also minimizes side reactions because it's able to just move things around directly, okay? So that is the role of pyruvate dehydrogenase and the role specifically of E2. Okay, problem 6, this is a simple problem, but it does require remembering a whole bunch of structures. So show both steps of the citrate synthase reaction. So this is just showing the steps. If you want to see the full mechanism of citrate synthase, go watch my video on the citric acid cycle. I covered all the mechanisms in that video for the citric acid cycle, but essentially just looking at the reactions, no mechanisms. Remember, we have oxaloacetate and acetyl coenzyme A. And notice how I numbered the carbons here. I numbered the carbons on acetyl coenzyme A, 1 and 2, then oxaloacetate 3, 4, 5, 6. That is because it is this carbon here that will be added to this carbonyl here, okay? So essentially, when this carbon is added here, so we get carbon 3 is now just a carboxylic acid that is off to the side. There's a bond formed between carbon 2 and carbon 4, and then carbon 1 is still attached to the coenzyme A. So this is called citryl coenzyme A. And then what happens is the coenzyme A leaves through a hydrolysis reaction with water, and then essentially now we have citrate. Citrate is a very easy structure to remember because you have a carboxylic acid group, carbon 1, carbon 4, you'll have carbon 3 attached to carbon 4, and then carbon 6. So you have carbon 2, 4, 5, and then carbon 1, 3, and 6 are your carboxylic acids. So citrate is also sometimes called tricarboxylic acid, tricarboxylate, that's where the TCA comes from. It's because it has 3 carboxylic acids. Also, there's an OH on carbon 4 that is formed as a result of the reduction of carbon 4 here. So the carbonyl gets turned into an OH group. All right, again, if you want to see the mechanism, check out the video on the citric acid cycle. All right. Question 7. So this is showing the mechanism of succinyl synthetase. So this I've already gone over again in my video on the citric acid cycle, but we will go over it again. So essentially, here we start out with succinyl coenzyme A, and in the active site, there is a histidine and a phosphate group. So the first thing that will happen is the OH on the phosphate group here will attack the carbonyl on succinyl CoA, and the electrons in this bond will go to the sulfur, and that will release the coenzyme A, okay? So now, instead of the coenzyme A, there is a phosphate group bound to the succinate, okay? So now bound to this carbonyl, there is a phosphate group. This group has a name. It's called a mixed anhydride, right? And this is very high in energy. It's very unstable. So the breaking down of this mixed anhydride will release a lot of energy, and that will be used to catalyze the reaction. Okay, so now that's where this histidine comes into play, right? We have the histidine here. Oh my goodness. Okay, so the electrons on this nitrogen, this lone pair on the nitrogen in the histidine, will come up, and it will attack the phosphorus in the phosphate group. And then the electrons here in this bond will go to this oxygen, okay? And then what that will do, that will generate a carboxylic acid group here, and then this compound here will be released as succinate, and then what will happen is, or the result of this will be a phosphorylated histidine. So now the phosphate is on the histidine. So what is going to happen now is that this phosphate is going to go to the ADP attached to the active site, and that will be used to make ATP. And what happens physically in this active site is this histidine will swing down. Oh my goodness, this marker's bad. The histidine will sort of swing. Okay. Can you read that? Nope. It will swing down, and then it will bring the phosphate group to the ADP, and then that will phosphorylate the ADP, making an ATP here, and that will regenerate the histidine. All right, so that is the mechanism of succinyl synthetase. All right, next question. What advantage does the glyoxylate cycle provide to plants and bacteria? So this is the glyoxylate cycle. It is sort of an alternative citric acid cycle. It takes place in the glyoxysome in plants. And essentially, it looks kind of like the citric acid cycle. We have oxaloacetate reacting with acetyl-CoA, makes citrate, isocitrate, then it makes glyoxylate and succinate. So that's new, okay? So isocitrate is going to turn into succinate and glyoxylate. Glyoxylate with another acetyl-CoA will be used to make malate, and malate can then get turned into oxaloacetate. So it's similar, but it's almost like it's kind of taking a shortcut through the citric acid cycle. So kind of what is the purpose of this? Well, where is all this acetyl-CoA coming from? So in the next biochemistry course, Biochemistry 2, you'll learn about fatty acid degradation, and you'll learn that fatty acids essentially, when they're degraded, turn into a bunch of acetyl coenzyme A. So fatty acid degradation produces acetyl coenzyme A, and those can enter the glyoxylate cycle to make succinate. So the succinate will then leave the cycle. It will enter the mitochondria, where it will enter the citric acid cycle. Citric acid cycle will produce malate, turning into oxaloacetate. Oxaloacetate, remember, can then enter gluconeogenesis, which we saw earlier, to produce glucose. Okay, so what is the purpose of this? So acetyl-CoA from fatty acid degradation. So if a lot of fatty acid degradation is going on, all that acetyl-CoA can be turned into glucose through this pathway. So acetyl-CoA goes through the glyoxylate cycle, produces succinate. Succinate enters the citric acid cycle, which then can form malate, oxaloacetate, and can go up to glucose to make, or can make glucose through gluconeogenesis. Through this process, no carbon is lost as CO2, so that's nice. Also, no ATP is used until gluconeogenesis, which of course requires ATP. So it is a way for bacteria and plants to convert a lot of acetyl-CoA from fatty acid degradation to make glucose. And it sort of represents an alternate pathway through the citric acid cycle. Okay, question 9. So this one is asking, what is the metabolic role of the electron transport chain and what is powering the enzymes? So the electron transport chain is converting electron motive force into proton motive force, and then that proton motive force is used to make ATP, right? So the electron motive force originally comes from the electrons from glucose. So the electrons in glucose are carrying a lot of energy. So in order to bring that energy to the electron transport chain, they are picked up by the electron carriers NADH and FADH2. So these will carry those electrons from glucose, bringing the electron motive force, the sort of energy carried by those electrons, to the electron transport chain, where that energy then gets converted into a proton motive force. What is proton motive force? This is a hydrogen ion H plus gradient between the inner mitochondrial membrane. So within the matrix, which is the inner part of the mitochondria, you have a low H plus concentration, and in the inner membrane space, you have a high H plus concentration. This concentration gradient is what powers ATP synthase, and the H plus gradient is generated. So this is made by the electron transport chain. Okay? So the proton motive force, this H plus gradient, allows for ATP production through ATP synthase. So the H plus are able to flow from the inner membrane space into the matrix, and they do so through ATP synthase, which acts as an H plus channel. As the H plus flow, that releases that energy and is used to generate ATP, okay? So, or phosphorylate an ADP to make ATP, making about 30-ish ATP per glucose, depending on some factors like the NADH shuttle used and the number of subunits in the C cylinder, all right? So what exactly is powering the enzymes of the electron transport chain? It is the electrons from NADH and FADH2, as well as the high electronegativity of oxygen that makes the whole process energetically favorable. The oxygen will accept the electrons at the end, and that is all energetically favorable because oxygen really wants those electrons, right? It really wants to be reduced, okay? So that is how the electron transport chain works. All right, question 10, we have a math problem. Calculate the free energy of the proton motive force if the matrix has pH equals 7 and the intermembrane space has pH equals 5, and the voltage difference is 0.14 volts. Okay, so essentially we know that the matrix has a low H plus concentration, so it'll have a higher pH. IMS, or intermembrane space, has a higher H plus concentration, so that will have a lower pH. So to solve this, we use this fun equation, delta G equals RT ln C2 divided by C1 plus Z times F times delta V. What does all that mean? R is the gas constant, 8.3145 joules per mole Kelvin. T is the temperature in Kelvin, so physiological temperature is 37 Celsius. So you add 273 to that, you get 310 Kelvin. Z is the charge, in this case on a hydrogen ion, so +1. F, Faraday's constant, 96.49 kilojoules per mole volt. And then, so now we are left with C2 and C1. Delta V is just the voltage difference, the difference in electric potential between both sides of the membrane, okay? So C2 and C1. So C2 is the concentration of H+, the H+ concentration where H+ is moved to. So we can see that the electron transport chain, when some energy from NADH or FADH2 enters, H+ are going to be pumped into the inner membrane space. So it is moved to the inner membrane space. C1 is the concentration where H+ is moved from. So it is moved from the matrix into the IMS. So this is from matrix. Okay? So in this case, C2 over C1. So C2 over C1 equals the concentration at the IMS versus, or divided by the concentration in the matrix. Yep. Okay. So the first thing we have to do is calculate those concentrations. So we have the pHs. So we know pH is equal to negative log H plus concentration. So then we can convert this into the H plus concentration is equal to 10 to the negative pH. So C2 is in the IMS. So C2, so the IMS has a pH of 5. So C2 IMS is equal to 10 to the minus 5, while C1, which is the matrix, is going to have a pH of, or sorry, a concentration of 10 to the minus 7. So pH of 7, 10 to the minus 7, okay? So now we can calculate this. We need to keep all the units consistent, so let's just convert everything into kilojoules. So in order to do that, we have delta G, I was going to take the whole board to write this, equals 8.3145 joules per mole Kelvin. It's readable, yep. Times, okay, so why am I timesing it? Why am I multiplying this? We're going to multiply it to convert joules into kilojoules. So in 1 kilojoule, there are 1,000 joules. Okay, R, T, 310 Kelvin. Should have started this lower, oh no. Okay, so now we have the ln of C2 over C1. So this is going to be 10 to the minus 5 over 10 to the minus 7. Okay, moving down here, let's do this. And then plus 1, that's our Z, times F. We can keep it the same because it's already in kilojoules. 96.49 kilojoule per mole volt times 0.14 volts. Oh, you cannot read that. Let me rewrite it. 96.49 kilojoules per mole times volts times 0.14 volts. Okay? So that's quite a long expression, but when you put this into your calculator, you get delta G is equal to positive 25 kilojoules. What does this mean? This means this is exergonic. It requires energy. So this is going to require energy to generate this membrane. And where does that energy come from? NADH and FADH2. All right, so that is how you do a problem like this. All right, now on to the next problem. Okay, question 11. So this is about the electron transport chain now. So what is the role of the Q cycle? What are the reactants and the final product? So the Q cycle takes place inside complex 3. I've gone over this already in more detail in my electron transport chain ATP synthase video. However, we'll go over it here again in a bit less detail, okay? So QH2 is going to be what enters this, and the role of this is to take 2 electrons from QH2 and bring them over to cytochrome C that can then carry them over to complex 4, okay? So essentially what's going to happen, the QH2 is going to come in from complex 1 or 2, and 1 electron is going to be passed to cytochrome C plus 3, and that will make that will reduce cytochrome C plus 3 and make cytochrome C plus 2. Cytochrome C plus 2 is carrying 1 electron that can then go to complex 4. doing this is only going to take one electron away from QH2, which QH2 is ubiquinol, and this will generate the semiquinone radical carrying one electron. So that electron has to go somewhere, and it gets passed to another Q. So then this generates one Q that will go off to complex 1 and 2 to be regenerated back into QH2. And this electron will get passed to a Q to make a semiquinone radical again. So the site at which the sort of oxidation of QH2 happens is the Q0 site, which has a high QH2 affinity but a low Q affinity. And at the QI site here, this is where Q here will be reduced. So it will be reduced to the semiquinone radical, and then when another electron comes through this, the semiquinone radical will then be converted back to a QH2. So this has a high Q affinity, low QH2 affinity. When a QH2 is regenerated here after 2 QH2 enter complex 3, so 2 QH2 enter complex 3, that regenerates 1 QH2 here, okay? And that 1 QH2 will then leave because of the low QH2 affinity, and will go back to re-enter complex 3 again, okay? So 2 QH2 are needed to fully reduce Q, and that will generate 2 cytochrome C plus 2. That will be carrying 2 electrons, and this will regenerate 1 QH2, also 2 electrons. Okay, and then the 4 QH2 will be carrying 4 electrons. Or sorry, yeah, 2 QH2 will carry 4 electrons. Okay, and 2 cytochrome Cs are needed in order to reduce the oxygen at the end of complex 4. Okay, so essentially the role is to generate cytochrome C plus 2, bring that to complex 4, and the reactants are 2 QH2, those are what enter, and what leaves is going to be 2 of the Qs, 1 QH2, and 2 cytochrome C. I should also add plus 2 Q. Those are going to leave from the, or sorry, no, it would be 1 Q. Wait, no. No. 2 Q. Sorry. So for every 1 QH2 that enters, 1 Q is generated here, and that will leave. Okay? So essentially this process runs twice, is what I'm trying to say. All right? So now let's move on to the next question. All right, next question. Question 12. This is another math problem. So this is a redox reaction we have going on here. A plus 2 plus B plus 3 converts into A plus 3 plus B plus 2. So what's going to happen here is the A plus 2 is going to get oxidized, the B plus 3 is going to be reduced, and the reduced form of A is A plus 3, and the oxidized form of A is A plus 3, the reduced form of B is B plus 2. So the electron will be going from A to B, okay? So the first thing we want to do is calculate the change in free energy, the delta G, for the reaction. To do that, we need the cell potential, the electric cell potential here, the delta E, okay? And this is just the difference in standard reduction potentials, but you don't need to calculate that here. We just know that the difference is negative 0.3 volts. Okay, so to calculate delta G, we use this equation, delta G equals negative NFE. F is the Faraday constant, 96.49 kilojoules per mole volt. N is the number of electrons transferred, so N equals number E minus transferred. And remember that the electron will be going from here to here, okay? That's essentially what's happening here. So in this case, it's just 1 electron, 1 E minus. Okay, so this is fairly straightforward. This is standard Gibbs free energy. So delta G at standard conditions is going to be equal to negative 1, so just 1 electron, so just 196.49 kilojoules per mole times volts times negative 0.30 volts. Okay, and what do you get? You get delta G, marker's dying again. delta G is equal to positive 29 kilojoules per mole. So this is non-spontaneous. This is endergonic. So this requires free energy. So this will not happen on its own. It requires an input of energy, okay? So now we can calculate K. To do this, delta G equals delta G standard plus RT ln K. Something that we know is that delta G is going to be equal to 0 because this reaction is at equilibrium. Okay, so we can then make this into delta G standard is equal to negative RT ln K. As we've seen in a previous problem, R is equal to 0.0083145 kilojoules per mole Kelvin. That is a 5. And again, sorry for the markers being a little bad. And T is equal to 310 Kelvin. Okay. The other thing we need to write down is that K is going to be equal to the products over the reactants. So concentration of A plus 3, B plus 2 over A plus 2, B plus 3. So products over reactants there. Okay. So now we have to rearrange this equation to solve for K. So what we're going to do is divide both sides by RT and then get rid of the ln by doing e to the power of both sides. So we get K is equal to e to the power of negative delta G standard over RT. Okay, so we get K is equal to e to the power of negative 29 kilojoule per mole over 0.0083145 kilojoule per mole Kelvin. And then this is all going to be multiplied by 310 Kelvin. Or the denominator will be multiplied by that. And then we get K is equal to 1.3 times 10 to the minus 5. So what does that mean? So remember, K is equal to the products over the reactants. So if this is less than 1, that means that there's more reactants than there are products. Does that make sense? Yes, delta G is positive, so the reaction is not energetically favorable. That means it's less likely to happen. So if the reaction is not likely to happen, it means that we're going to have more of the reactants than we will products, which is what our K tells us. Okay? So, next problem. All right, question 13. How did the experiments with ATP synthase and bacteriorhodopsin confirm the chemiosmotic hypothesis? So the chemiosmotic hypothesis is just that essentially what we saw earlier, the electron motive force and the electron transport chain is used to generate a proton motive force. Proton motive force allows ATP synthase to make ATP. Okay? So the way this was carried out, so what is bacteriorhodopsin? It is a light-driven, this is wrong, light-driven H plus pump. So what is going to happen is when light shines on the bacteriorhodopsin, the energy from light is used to pump H plus into the synthetic vesicle. So if the synthetic vesicle has bacteriorhodopsin and ATP synthase in it. So what this does is it creates an H plus gradient. Inside the vesicle, high H plus, much like in the inner membrane space. Outside the vesicle, low H plus, much like in the matrix. Okay? And then what was found is that ATP synthase makes ATP when these vesicles are exposed to light. Why? Because the bacteriorhodopsin, when exposed to light, pumps H plus into the vesicle, and then that H plus inside the vesicle leaves the vesicle down its concentration gradient through ATP synthase. And by doing so, ATP synthase will make ATP, right? So essentially what this shows is that the pump is going to generate proton motive force, and the proton motive force leads to ATP synthesis. So essentially, the electron transport chain and the ATP synthase are distinct, but they're linked by the PMF. This shows that the electron transport chain, through making an H plus gradient, that H plus gradient is what drives ATP synthase. It's not the electron transport chain directly. It is the electron transport chain generating the H plus gradient, and then that H plus gradient is used to make ATP through ATP synthase. Okay, so that is the experiment that confirmed the chemiosmotic hypothesis. All right, so question 14. So this one is about ATP synthase. So the first part is asking what beta unit of ATP synthase has the lowest ATP affinity and the highest ATP affinity. So the lowest affinity will be O, and the highest affinity will be T. That is because the O form releases ATP, and the T form, what that's going to do is it's going to convert ADP into ATP. Okay, but the L also has a low ATP affinity because that's what's picking up ADP, not ATP. Okay, and then the next part is asking how does the gamma subunit drive ATP formation? So the gamma subunit is in the center of the alpha 3 beta 3 hexamer, also called the F1 subunit, where the ATP is made. So the gamma subunit is going to rotate with the C cylinder in the counterclockwise direction. So whenever a proton enters the C cylinder, it causes the C cylinder to rotate counterclockwise, and that also rotates gamma counterclockwise. And then what's going to happen is that is going to not rotate the beta subunits. No, they're not going to rotate physically. Instead, they are going to change their conformation and their activity and their affinities for ATP. Okay, and they're going to go from L to T to O and then back to L. So looking at this, let's go through one cycle of this. So this one is going to start as an L. It's going to pick up an ADP, okay? L loose, picking up an ADP. And then what's going to happen is as this rotates counterclockwise, see how this has a little spine, and the spine corresponds to the T? So now this is going to move in, and then it's going to make this subunit look like this subunit, changing it from an L to a T. Okay, so once it's a T, the ADP will be converted to ATP, and then it'll rotate one more time, and then this end will be over here. So this one will make this look like an O subunit, and then the O subunit, or the O conformation, will is the open conformation. It will release the ATP. Okay, so as the gamma subunit rotates, what it does is it changes the conformation of the beta subunits from an L, which picks up ADP, to a T, which turns ADP into ATP, to an O, which releases the ATP. All right, 2 more questions. Question 15, almost done. How does thermogenin, or UCP1, generate heat? So UCP1 acts as an uncoupler. So this is going to uncouple the electron transport chain from ATP synthase. So essentially, electrons are going to flow through UCP1 instead of through the electron transport chain. And when they flow through UCP1, that is what generates heat, okay? So the electrons are going to go through UCP1, and that will release heat, okay? What's also important about this is that UCP1 acts as a proton channel. So essentially, when the electrons flow through here, the protons are going to be pumped into the matrix, versus the electron transport chain, which pumps protons into the intermembrane space. So you see when these are going in opposing directions, there's no net proton gradient anymore, because the protons are going in one direction here and in another direction here, so those cancel out. There's no more proton motive force, thus ATP synthase can't function. So essentially, you can think of it in a way that the energy from the proton motive force, or that would be used to make proton motive force, is instead being dissipated in order to release heat. Okay? Final question. We have made it to the last question of the practice final. Okay? This is a fun question. How does carbohydrate loading help long distance runners? So carbohydrate loading is you just eat a bunch of carbohydrates before a run, okay, like rice or pasta or something like that. And what this does is it spikes your blood sugar. It increases your blood glucose by a lot, and that causes the release of insulin. And if we remember to the video I did on glycogen metabolism regulation, increasing insulin activates glycogen synthase, which activates glycogen synthesis. So you're building up a big stock of glycogen before you run. And then when you're running, you're using a lot of ATP, so you increase AMP in your skeletal muscle. So increase in AMP does a lot of things, if we remember, but one thing it does is it activates glycogen phosphorylase allosterically. Remember, that's turning it from the T state to the R state. So that degrades glycogen. That's going to increase the amount of glucose in the cell, which will also increase the rate of glycolysis. AMP will also allosterically increase the rate of glycolysis too. So a lot of glycolysis that also feeds into the citric acid cycle, where you'll also see an increase due to some allosteric regulation there. Okay, so increased glycolysis, increased TCA, the overall result is an increase in ATP. So essentially, by storing a lot of energy in glycogen, when you're running, you now have more of an energy reserve that you can use, more ATP, more muscle contractions. Okay, so that is it for this practice final. There is one more video in this tutorial series. It will be another practice final, and that will be it for my CHEM271 tutorials. Thank you so much for watching. See you next time.